Welcome to iLecture Online, and here's an example of how to do a physics problem dealing with electrical potential energy and electrical potential. So the problem we're looking at today is as follows. A uniform electric field of 250 newtons per coulomb is directed in the positive x direction. A 12 microcoulomb charge is pushed from x equals 2 meters to the origin. How much work is required? What is the potential difference between the 2 points? All right, where do we start? Well, the first thing we always want to do is draw a nice little diagram to get a feel of what's really happening. So how do we have a uniform electric field? Well, it says that it's directed in the positive x direction, so let's indicate that by drawing some arrows in the positive x direction representing the electric field. Now, typically speaking, the reason why there's an electric field there is there's probably an excess of positive charges on the left side, and there's probably an excess of negative charges on the right side, and that's usually why we have an electric field. So let's say that here this is at origin, x equals 0, and here this is x equals 2 meters. We now have a 12 microcoulomb charge, and it looks like it's a positive charge, so let's place it right here at x equals 2 meters, positive charge. Q is equal to 12 microcoulombs. Micro is 10 to the minus 6 coulombs. And now we're pushing this all the way to the origin. So we're giving it a push with some force F and bringing it all the way over to the other side until we reach the other side at the origin. And the question is how much work is required to do that. Also, let's write down the strength of the electric field. The electric field strength is equal to 250 newtons per coulomb. All right, so let's go ahead and start. The definition of work done is force times distance times the cosine of the angle between them. Now, if we're looking at this chart right here, and let me get some color pens, we can see that we have a force pushing to the right, like this, and the direction of motion is also in the same direction. So we're moving in the negative x direction, we're pushing in this direction. Since they're both in the same direction, the work done will be positive. And how much force do we need to push the charge across? Well, from definition, we know that the strength of the electric field is equal to the ratio of the force that is exerted on the charge divided by the size of the charge, Q, which means that the force we need is equal to the strength of the electric field times the charge Q. So we can replace the force here by F times Q, and then of course times D. That's the work done. Now, how much force does it require? This is EQD. So plugging in for E, this is equal to 250 newtons per coulomb times the charge. The charge is 12 microcoulombs, 12 times 10 to the minus 6 coulombs. And then the distance is a distance of 2 meters. And you can see here that the coulombs will cancel out, and we end up with Newton meters. And of course, the units of Newton meters is joules. We now grab our calculator. And let's see how much that is. So we have 250 times 12e to the 6 minus times 2, and we have 6 times 10 to the minus 3. This is equal to 6 times 10 to the minus 3 joules, or 6 millijoules. And that's the amount of work required to push that charge across the 2 meters through that electric field. All right, now it says, what is the potential difference between the 2 points? What is the potential difference between x equals 2 meters and x equals 0? Since, of course, the positive charge is over here, this should be at a higher potential. The negative charge is over here, that will be at a lower potential. And the definition of potential difference, delta V, is equal to the work done to push a charge across that distance divided by the size of the charge. So in this case, the work done is equal to 6 times 10 to the minus 3 joules, and the charge is equal to 12 times 10 to the minus 6 coulombs. And so joules per coulomb, the unit of that is volts. And if we throw that into our calculator, so we divide that by 12e to the 6 minus equals, and so that's equal to 500 volts. delta V, the potential difference, is 500 volts, which means that at x equals 0, the potential is 500 volts higher than x equals 2 meters. So if at x equals 2 meters, the potential V is equal to 0 volts, then over here the potential would be equal to 500 volts higher, or 500 volts. And that's how you do that problem. All right, let's come up with some more examples to get a better feel of what this is all about.